In this video, we are going to talk about gas stoichiometry. Remember, stoichiometry is basically just a way of being able to calculate mass and moles of products and reactants in a chemical equation. Well, gases can be calculated in a similar fashion, but we have to put a few givens down first. So let's go ahead and um, define some things. So gas stoichiometry. So gases are normally measured in their volume, and normally we are measuring gases in terms of liters. So a gas at something called, we'll go ahead and say standard temperature and pressure. So standard temperature and pressure. So standard temperature and pressure. The standard temperature is at something called 273 degrees Kelvin. Kelvin is a unit of measurement it's the SI unit for temperature, and the pressure is going to be at 1 atmosphere. Later on, we'll take a look at what exactly this means. And actually, this would be equal to 0 degrees Celsius. But later on, when we actually look at gases and study them, we'll look at this in more detail, and as far as pressures go too. But just know that if you ever hear standard temperature and pressure, and it's often abbreviated just with STP. So STP stands for standard temperature and pressure. The standard temperature is 273. The standard pressure for a gas is 1 atmosphere. So the thing that we need to know about gases in terms of stoichiometry means that any gas, so any gas meaning helium, nitrogen, um, argon, so any gas at STP, and STP once again meaning standard temperature and pressure at 273 K or 1 atmosphere. So any gas at standard temperature and pressure occupies 22.4 liters. So here's another, or any gas at STP occupies 22.4 liters if you have 1 mole. If you have 1 mole of the gas. Have 1 mole of the gas. So this is another conversion factor, if you will, between our moles and liters. So this is used for gas. So if I have 1 mole of any gas, so 1 mole of any gas at STP occupies 22.4 liters. Okay, so we're going to use this conversion factor to go ahead and to do a couple of problems. So let's go ahead and scroll down. So it says, what volume of oxygen is needed to react with solid sulfur to form 3.5 liters of SO2? Well, the first thing that we need to do, the first important thing, is to go ahead and get our balanced chemical equation. So it says, what volume of oxygen? So oxygen is going to be a reactant, so I'm going to go ahead and say O2. Now, oxygen, remember, is diatomic. Oxygen is not mixed with anything here, so it's just by itself. So oxygen gas is always O2. So we're going to say O2 plus needed to react with solid sulfur. So sulfur is just an element. It's not a diatomic element, so it's just S. So O2 plus S, and then we're going to have yield, and SO2 is covalent, so we're going to call that sulfur dioxide, but we'll just say SO2. Alright, so let's go ahead and double check, make sure everything's balanced. I have 2 oxygens on the left, 2 oxygens on the right, 1 sulfur on the left, 1 sulfur on the right. So we got lucky in this one. This is a balanced equation as we have written it. So we'll go ahead and solve these using dimensional analysis or the factor label. We've also called these the fence post problems. So let's go ahead and start out with what they've given us. They've given us 3.5 liters of SO2, sulfur dioxide. So we'll go ahead and draw this out for our fence post. So now we have to look at what unit we want to go to. It says what volume of oxygen. So volume is measured in liters. So basically, let's try a different color here. We'll put this on the right. So we're looking for liters of O2. So basically, this is the unit that we're going for, liters of O2, because it says what volume of oxygen, and oxygen is measured, or volume is measured in liters. So let's go ahead and choose our teal color again, or Carolina blue. So I want to cancel out liters of SO2, so I'm going to put liters of SO2 in the bottom. But now let's scroll back up to the top. We said that any gas at STP occupies 22.4 liters. Okay, so we're assuming that all of these are at STP. So what this means is that if I have 22.4 liters of SO2, that is 1 mole of SO2, sulfur dioxide. Okay, so here my liters on the bottom will cancel out with these liters. I'm left with moles of SO2, but I don't want moles of SO2. I ultimately want liters of O2. So I'm going to go ahead and put moles of SO2 on the bottom. So now this particular conversion factor comes from our balanced equation. So if we go up to here, we're going to have 1 mole or 1 mole on the right of sulfur dioxide, okay, and we want to go to oxygen is 1 mole of oxygen on the left. So from this number here, well, there's no number, but it's assumed to be 1. With the SO2, the same thing, there's no number, but it's assumed to be 1. It's a 1-to-1 ratio. So I know that 1 mole of O2 is equal to 1 mole of SO2, and I know this from this balanced equation. Once again, we got lucky and it was balanced. So now, let's pick a different color. So now, liters of SO2 cancels out liters of SO2. Moles of SO2 cancels out moles of SO2. I'm left with moles of O2, but I want to go to liters of O2, so I know I've got to do one more step. So we'll go ahead and extend this out. So to cancel out moles of O2, I'll put moles of O2 on the bottom. So 1 mole of O2, remember at STP, 1 mole of any gas occupies a volume of 22.4 liters of O2. So now, what's canceling? The moles of O2 cancel, the moles of O2 cancel. I'm left with liters of O2, which is good because that's the unit that I wanted, liters of O2. Now to solve this, all I do is I multiply everything on top, 3.5 times 1 times 1 times 22.4, and divide that by everything multiplied on bottom. So I'm going to say 22.4 times 1 times 1. Okay, so if I just take a quick look at this, I know that that will cancel that one out. So ultimately, when you figure this out, I don't want to say cancel too much because that's going to maybe confuse some of you, but just work these out the way that we've been doing them in class and the way that you know how. You take everything on top, multiply it together, you'll get a number, and then take everything multiplied together on bottom and get a number. And when you do this, you actually come out to get 3.5 liters of O2. So that's your answer, 3.5 liters of oxygen gas. So let's scroll down and we'll do one more example. So here it says how many liters of propane gas will undergo complete combustion with 34 liters of oxygen gas. So just like before, the first thing that we need to do is we need to write a balanced chemical equation. So let's start out with our propane gas, which is C3H8. Now remember, a complete combustion reaction means the hydrocarbon that we have, in this case it's propane. So the hydrocarbon is always mixed with oxygen, and the complete combustion of a hydrocarbon, my products are always carbon dioxide, CO2, and water, H2O. So now let's go through and make sure this is balanced. So on the left I have 3 carbons, on the right I have 1 carbon. So if I put a 3 in front of this, that will balance out my carbons. So then take a look at hydrogen. I have 8 hydrogens on the left. I have 2 hydrogens on the right. So if I put a coefficient of 4 here, this is going to give me 8 hydrogens on the right. And now if I double check my oxygens, let's go ahead and count. 3 times 2, that's going to give me 6 O's here. And then if I double check this, 4 times the 1, that's going to give me 4 O's here for a total of 10 oxygens on the right. In order to make this 10 oxygens, I got to put a 5 in front of that. So now, this is a balanced equation just like it is. So now let's go ahead and set up what they give us. So they give us 34 liters of oxygen gas. So let's choose a different color. We'll choose orange this time. So we'll say 34 liters of O2. That's what we started with, and we're going to do another fence post problem. And we know the unit we want to end up with is liters of propane gas. So basically we're looking for liters of C3H8. Okay, so liters of C3H8. So let's go ahead and start counting out our liters of O2. So I'm going to put liters of O2 on the bottom, and then I'm going to say 1 mole of O2 on top. So I know that 1 mole of any gas at STP, and once again we're assuming that all of these are at standard temperature and pressure, occupies 22.4 liters. So now I'm left with moles of O2, so I need to keep going. So I've got moles. Let's try that a little neater. So I've got moles of O2 on the bottom, and so this particular conversion factor is going to come from our balanced equation. So moles of O2, so I have 5 moles of O2 to every 1 mole of propane, which is C3H8. Alright, let's scroll back up a little bit for some room. Okay, so now the units I have are moles of C3H8, but I want liters, so I got to go one more time. So I'm going to say 1 mole of C3H8, and once again I know that any gas at STP, if I have 1 mole of it, occupies 22.4 liters of C3H8. So now let's go ahead and cross out some things. My liters here will cancel out with liters of O2. Moles of O2 cancels out moles of O2. Moles of propane cancels out moles of propane. And I'm left with liters of C3H8, which is propane, so that's what I wanted. I wanted liters of C3H8. So now the next thing I do is I take everything on top, I multiply it together, and I'll get some number here, and then I take everything together, multiply it on the bottom, then I'll get another number, and then I'll take my numerator number divided by my denominator number, and basically when you do this, you're actually just ending up with 34 divided by 5, and the final answer for this is going to give you 6.8 liters of C3H8, which is your propane. So this is your final answer, 6.8 liters of propane.